Hello everyone. Today's animated PowerPoint is on metamorphic rocks. And now that we've covered igneous and sedimentary rocks, we're in a much better position to understand what metamorphic rocks are all about. So up here towards the top of the slide, here's a quick definition of metamorphic rocks and the metamorphic process. Metamorphic rocks and metamorphism are all about change and transformation. However, whatever we do to the rock, it has to occur in the solid state. In other words, we're not allowed to melt the rock during metamorphism. And that kind of makes sense if you think about it, because if we do melt the rock, we then have magma. And if that magma cools and crystallizes, it'll become an igneous rock. So we've left the metamorphic rock realm altogether. Bottom line here, metamorphism is all about solid state change. What factors bring about that change? We'll get into this more in the next slide, but very briefly for this slide, it has to do with heat associated with elevated temperatures, elevated pressures, and also hot watery fluids sort of percolating and migrating through the rock. Metamorphic rocks can be divided up into two main categories called foliated and non-foliated metamorphic rocks. We'll get into this more in a couple slides, but for now, just appreciate that foliated rocks refer to the alignment of minerals in the rock. Okay, so we're now going to go over different ways that pressure can be applied and how Mother Nature applies that pressure during the metamorphic process is ultimately what influences whether the metamorphic rock will become foliated or non-foliated. So let's start over here on the left, and let's imagine that we're squeezing the rock equally in all directions. Now at first, maybe we have a rock like granite, for example. So the minerals in the rock, represented by these black bars, aren't aligned. They're just randomly oriented. You can probably appreciate if we squeeze the rock equally in all directions, certainly the volume will be reduced and the density, that is the mass to volume ratio, will increase. But at the end of the day, we're not going to see any mineral alignment if we're careful to squeeze the rock equally in all directions. If the minerals were randomly arranged to begin with, then after the squeezing, if it's equal in all directions, the minerals are still going to be randomly oriented, as you can see here. Let's imagine now instead the right-hand diagram where maybe we're at a convergent plate boundary, for example, and now we are squeezing the rock harder in one direction than in any other direction. Notice in the right-hand diagram, we're still squeezing the rock in all directions. We're just doing it more in the vertical direction in this case. And the main difference here is that whereas the minerals in the rock perhaps still start out being randomly arranged as a result of this unequal pressure, and that unequal pressure, by the way, is called stress. As a result of stress, the minerals now align. They kind of come into subparallel alignment within the rock. That stress-induced alignment in the metamorphic rock is known as foliation. And that's a very important distinction among metamorphic rocks, whether they're foliated or not. Here's a quick slide just to illustrate a few of the ways that foliation can actually develop in the rock as the minerals are becoming aligned. One way is when material in an individual mineral, an individual crystal, is dissolved away and those atoms migrate to other portions of the same crystal. And this can ultimately cause the crystal to change shape. Imagine that we have, in this simplistic example, an initially spherical crystal. And if we remove material from the top and bottom of the crystal and then redeposit those atoms on the sides of the crystal, that's one way that we can get the crystal to change shape. That's known as dissolution and chemical precipitation or chemical deposition. Another way maybe is more obvious, and that's simply plastic flow. Typically, metamorphism tends to occur at depth within Earth's interior, at depths of perhaps a kilometer or more. And at those depths, very often the rock, although it's not melted yet, it still might be a little bit plastic, particularly at geologic timescales. And so in the same way that we can change the shape of a ball of silly putty by squeezing it, subjecting it to stress as opposed to pressure, we can align the minerals in a metamorphic rock just by getting the rock to flow plastically. And then finally, or thirdly, I should say, grain rotation can sometimes bring about foliation. So in this case, again, we have kind of randomly oriented minerals in the rock, and as a result of squeezing, the minerals will tend to rotate in a direction that tends to be perpendicular to the direction of squeezing. That's known as grain rotation. And then finally, over there in the lower right, we have recrystallization. So what's happening here is that pre-existing minerals in the rock actually get destroyed as the rock experiences different pressures and temperatures than those at which it formed. There are certain minerals in the rock that are going to become unstable. So those minerals go away, they get destroyed, and in their place, new minerals grow using the same atoms, but they grow in alignment in this case. And again, the rule of thumb between compressive stress and foliation is that the foliation in a metamorphic rock typically develops in a direction perpendicular to that of the maximum compressive stress. Okay, so just to summarize, and I'm not really going to emphasize this slide too much, I just want you to appreciate that there are different ways, there are different mechanisms for how foliation can actually develop in metamorphic rocks. Well, what happens during the metamorphic process? There are certain factors that influence how a rock changes. These are called metamorphic controls. And then there are specific changes that accompany the metamorphic process, listed over here in the right-hand column. Particularly for metamorphic controls listed on the left, we can make a nice analogy with cooking. So imagine cooking something at low temperature versus high temperature. Whatever you're cooking is going to come out very differently depending on the temperature at which you cook it. It's the same with metamorphism and metamorphic rocks. As we'll see, rocks that are subjected to low temperature metamorphism come out very differently than those subjected to high temperature metamorphism. And the same is true with pressure and also stress. Those rocks and those foods, frankly, subjected to low pressures come out very differently than those subjected to high pressures, and in the case of metamorphism, high stresses. In both cooking and metamorphism, hot, watery fluids can sometimes play a role. Imagine how an egg comes out when you poach it in the presence of water versus when you fry it in the absence of water. And then finally, or fourthly, I should say, what you start with influences what you end up with both in metamorphism and in cooking. Hey, if you take a bunch of flour, add some sugar, mix in some milk and eggs, throw it in the oven, and bake it at a certain temperature for a while, you have a cake. On the other hand, if you throw in a bunch of vegetables in a pot with maybe some tomato sauce and some spices and a whole bunch of beans, and you cook it differently than you would the cake, you end up with soup or chili. So the point is that in both metamorphism and in cooking, the starting ingredients influence what you end up with. And then finally, in both metamorphism and cooking, time plays a role. If you cook a cake for too long, it comes out to be a charred brick. On the other hand, if you don't cook the cake enough, it comes out watery and moist. Same with metamorphism. Metamorphic rocks that are cooked and squeezed for a longer amount of time will sometimes come out differently than those that are cooked and squeezed for a shorter amount of time. Okay, when it comes to the changes associated with metamorphism, we've kind of mentioned recrystallization in the last slide. A lot of times what happens inside the rock in the solid state, so the rock isn't melting, is that pre-existing minerals are destroyed and new minerals grow. So we're not creating entirely new minerals that weren't there before. We're actually recrystallizing new minerals by destroying old minerals. We also mentioned too that depending on how the pressure is applied during metamorphism, foliation, that is stress-induced mineral alignment, may or may not develop. Also, generally speaking, because we're squeezing the rock typically, the density of the rock will increase during metamorphism. And sometimes anyway, the metamorphic process is associated with water loss. Not always, however. In a subsequent slide, we'll see an example of how metamorphism can occur in water-rich environments where the water actually absorbs rock during the metamorphic process. In the same way that we earlier spoke of igneous textures, we can speak of metamorphic textures, particularly textures associated with foliated metamorphic rocks. Remember that texture in this case doesn't mean whether the rock is smooth or rough. It refers to the characteristics of the rock components, specifically the minerals. And in this case, it refers to the size of the crystals and also how specifically those crystals are aligned and the overall characteristics of the rock and the crystals in the rock. So slaty rock cleavage results from relatively mild metamorphism. It results in a very fine-grained rock called slate. And as we'll see in the next slide, slate has a characteristic that it tends to split very easily along closely spaced foliation planes. Phylitic texture is a result of slightly more intense metamorphism. It still causes the rock to recrystallize into a fine-grained state, but in contrast to slate or slaty rock cleavage, a rock with a phylitic texture, as we'll see, has kind of a dull waxy sheen because the crystals are a little bit larger in the rock and they reflect a little bit more light than in the case of the very, very small crystals in slate. Schistosity and gneissic texture are associated with more intense metamorphism, and at this point, the rocks become visibly grainy, meaning you can actually see the crystals. And that's true both for schistosity and also rocks that have a gneissic texture. The main difference is that in a schist that obviously has the characteristic of a schistose texture, or we can also say schistosity, we can see visible alignment of the minerals, as I'll show you in a minute, but we don't necessarily see any light and dark banding in the rock. Whereas when we have a rock with a gneissic texture, we absolutely see light and dark compositional banding. So just a quick summary, these are the four foliated metamorphic rocks you want to be familiar with: slate, phyllite, schist, and gneiss. Now I want to go through each one of these. Here are a couple of photographs of slate. This is what slate looks like under a microscope. You can see, based on the scale here, slate is a very, very fine-grained rock. Even under high-power magnification, it's difficult to see individual crystals in a piece of slate. This is what slate looks like in outcrop. This is a slate quarry. And you can kind of see down here the closely spaced foliation planes. That's what causes slate to split easily along those foliation planes. And for that reason, it's used as decorative stone and building stone because of its ability to split easily along those foliation planes. So slate can be used as roofing tiles, for example, and it can also be used to make pool tables. If you were to cut away the felt on this pool table, underneath that felt, you would see a very expensive piece of slate. And what we're looking at here is a foliation surface that results from splitting a piece of slate into thinner pieces. This is phyllite. You can see superficially it looks a lot like slate. It's fine-grained, but at this point now the crystals are a little bit larger than they were for slate. The main way to distinguish phyllite from slate is that in the case of phyllite, you can see it has sort of a dull sheen to it, a little bit of a shininess. And that's because the crystals in the rock are just a little bit larger, and they're actually beginning to reflect light at this point. So that's what creates that, that sort of dull sheen that we see in the case of phyllite. What I'll always do on an exam, for example, is I'll refer to slate as very fine-grained, and I'll refer to phyllite as just fine-grained. Once we get to schist, the rock is visibly medium to coarse-grained, meaning you can see individual crystals, although that photograph to the upper right is what schist looks like under a microscope, for example. You can still see the crystals in schist without a microscope. And in the main photo here, these individual sort of white patches are muscovite crystals, are mica crystals that kind of are aligned in the rock like dominoes or roofing shingles or fish scales. So we see this sort of scaly texture in schist. Here's an actual example of a schist unit exposed around Julian, hence the name Julian schist. And in this photograph, you can kind of see the edge of the road over here. You can see the foliation in the schist. There it is. And again, the rule of thumb with foliation is that the direction of maximum compressive stress is typically at a 90-degree angle to the foliation direction. Here's what nice looks like. Notice that the G is silent, so we pronounce this nice rather than gneiss. So the G is silent. You not only get this dramatic foliation in the rock due to alignment of minerals like quartz and feldspar, but you also get light and dark banding in the rock. And you can see in this photograph, some bands are really dark, whereas other bands tend to be light. So that's the main difference between schist and gneiss. Gneiss is banded, as you can see here, and schist is not. And both schist and gneiss tend to be medium to coarse-grained. So there's the foliation. And remember the rule that we developed: can you infer the direction of maximum compressive stress that produced this foliation? I'll bet by now you can. So there's the direction of maximum compressive stress. And again, the rule of thumb is it tends to be perpendicular. It tends to occur at a 90-degree angle with respect to the plane of foliation. Okay, just a reminder that in general, when we delve into Earth's interior, the deeper you go, the higher the pressure becomes, and also the deeper you go, the higher the temperatures become. What this means is that rocks that are metamorphosed at a greater depth are going to look differently than rocks that are metamorphosed at a shallower depth. It turns out that metamorphism can be progressive, particularly among foliated rocks. What this means is quite literally that maybe we start out with a shale, which of course is a sedimentary rock, that's a non-metamorphic rock, and upon mild metamorphism, that shale will turn into a slate. But we can keep going. If we take that slate and send it deeper down into a subduction zone, for example, that slate might literally transform into a phyllite, and so on and so forth. With even greater subduction, that phyllite may transform into a schist, and ultimately that schist can even transform into a gneiss. So the take-home message here is that with increasing pressure or stress and depth, metamorphic grade, that is the intensity of metamorphism, will increase, and that changing intensity can literally turn one type of foliated metamorphic rock into another, and another, and another. In general, as well, as we saw in the previous slides, with progressive metamorphism, the general rule is that grain size tends to increase. So if I get rid of some of this annotation here, you can perhaps better see it. That makes sense, right? Schist and gneiss are coarser grained than slate and phyllite. Their coarser grain size is an indication that they've been metamorphosed more intensely than slate and phyllite. And so in this case, we say that schist and gneiss are characteristic of a higher metamorphic grade than slate and phyllite. Okay, on to non-foliated metamorphic rocks. The four that I'd like you to be familiar with include marble, quartzite, serpentinite, and anthracite. Let's look at these briefly one at a time. So here's marble. You can see marble is typically a medium to coarse-grained, non-foliated metamorphic rock. We're not seeing any foliation in this specimen. And the main mineral in marble is the mineral calcite. CaCO3. And calcite is nothing other than metamorphosed limestone. In this case, the starting rock, limestone, is called the protolith. Think of the protolith as the parent rock that becomes metamorphosed, in this case, into marble. So marble has a limestone protolith, in other words. If you take limestone, which you know by now is a chemical sedimentary rock, and you subject that limestone to increased pressures and temperatures, it doesn't really change the rock in terms of mineralogy. We don't necessarily see new kinds of minerals growing in the rock that weren't there before. Instead, what tends to happen is the existing calcite crystals in the limestone tend to grow larger, and they develop these sort of interlocking grains that are sometimes referred to as having sutured grain boundaries. So in this example, the mineralogy of the rock is not changing during metamorphism, but the texture of the rock is changing. Typically, existing crystals in the rock, calcite in this case, grow larger during the metamorphic process. Here's another example of metamorphosed quartz sandstone. That's called quartzite. You can kind of see here that quartzite has a visibly grainy texture. And again, in this case, the quartz sandstone would be the protolith. And when quartz sandstone is metamorphosed, it turns into quartzite. And just like we saw with marble, if you look at quartzite under a microscope, you can see these interlocking crystals of quartz, otherwise known as sutured grain boundaries. Serpentinite is sort of a mottled green-colored rock, and it's essentially what mafic and ultramafic igneous rocks turn into when they're metamorphosed in the presence of water. So you would say in this case that the protolith for serpentinite might be a mafic rock like gabbro, for example, or even an ultramafic mantle rock like peridotite. And these mafic and ultramafic igneous rocks, when they become metamorphosed in the presence of abundant water, they can sometimes turn into serpentinite. What's kind of interesting about serpentinite, particularly in Northern California and Central California, there's a lot of this. It's associated with an ancient subduction zone up there. Serpentinite happens to be the California state rock. And then finally, anthracite. Anthracite is nothing other than metamorphic coal. And what's kind of interesting about anthracite is it has a glassy texture. It kind of looks like obsidian, except that it's not. You can easily tell this when you heft the sample in your hand. And if we were on campus, I would pass around a sample of anthracite, and you'd be able to tell very easily that this is not obsidian. It's softer than obsidian, for one thing, and also it's a lot lighter than obsidian when you heft equal volume pieces in your hand. That is to say that the density of anthracite is a lot lower than the density of obsidian. But in this case, coal is the protolith that metamorphoses into anthracite. So again, anthracite's just metamorphic coal. Okay, here's a quick concept check question. Which of the metamorphic rock specimens below are foliated? So I'll give you 5 seconds or so to decide. I'm hoping by now that the answer will be pretty obvious. Okay, did you decide? Well, pretty clear, right? Which ones are the foliated rocks? That's a piece of gneiss. You can clearly see the banding. This sort of sparkly rock down here, there's a little bit of a gneissic texture to this rock as well. So we could get away with calling the rock in the lower left-hand corner a gneiss as well, although it has sort of the fish scaly appearance as well. So we might actually describe the rock in the lower left corner as being a schistose gneiss, or perhaps a gneissic schist. Sometimes there's not a clear distinction between one type of foliation and another. And then obviously down here, we're dealing with a very fine-grained rock with very closely spaced foliation planes. Can you name that rock? Maybe you can. That would be slate. This is a piece of marble. That's not foliated. And this is a piece of anthracite. That's not foliated either. Here's another concept question. Would you expect foliated metamorphic rocks to form at depth at or near a plate boundary? So I'll give you a little bit of time to decide on what you think the right answer is. Okay, let's work through this. Would you expect foliated metamorphic rocks to form at depth at or near a plate boundary? What about A? No, because plate boundaries aren't associated with increased stress in comparison with plate interiors. Well, that's not true. Of course they are. If, for example, we're squeezing the rocks at a convergent plate boundary, that's exactly the type of environment where we're going to develop foliated rocks in response to a lot of compressive stress. What about B? Would we get foliated metamorphic rocks at depth near a plate boundary? Yes, we would, because all metamorphic rocks are foliated. No, that's not true. Clearly, some are and some aren't. What about C? No, we wouldn't expect foliated rocks because pre-existing rocks always melt at plate boundaries. Well, that's just not true either. No, they don't. So the answer is D. Yes, we would expect foliated metamorphic rocks to form at depth at or near a plate boundary, because down there at depth, beneath the plate boundary, we have high pressure and perhaps also high stress especially, and also high temperature. Those are exactly the conditions you need to foliate pre-existing rock. And here's another concept check. So imagine we have an igneous intrusion of hot magma right here. kind of in the lower right, as shown in cross-section, which sequence of foliated metamorphic rocks would develop with increasing proximity to the magma body, moving from point 1 to point 4. So again, I'll give you a few seconds to decide which answer you think is correct. Okay, what do you think? I put this one in here just to emphasize the progressive nature of metamorphism. A few slides back, we actually covered this. And the thing to appreciate about this diagram is notice that as we get closer and closer and closer and closer to the magma body, we're also getting deeper and deeper and deeper. In other words, as we approach the magma body, moving from point 1 to point 4, both pressure and temperature are increasing. So in this case then, all we want to do is arrange the rocks in order of increasing metamorphic intensity, that is increasing metamorphic grade, and the right answer is C. At point 1, we might at that point have turned our shale perhaps into a slate. And then at point 2, that slate has now turned into a phyllite. At point 3, the phyllite has become a schist. And at point 4, before the rock actually melts, maybe the schist has become a gneiss. On to something called metamorphic facies. And before I get to the facies concept, I just want you to appreciate that within a metamorphic rock, as pressures and temperatures are changing, we're going to see the growth of certain minerals that are characteristic of those new pressures and temperatures. Those are called index minerals. And the great thing about index minerals is they act literally as tiny pressure gauges and tiny thermometers in the rock. And because we can grow these index minerals in the lab, we know that when we find some kind of metamorphic rock with certain index minerals, we have a pretty good understanding at that point of the temperature and pressure history of the rock because of the index minerals in the rock. And so what we mean by a metamorphic facies is essentially a specific set of pressures and temperatures we can infer about the history of the rock based on its index minerals. So let me show you in practice how we would use this concept to learn more about metamorphic rocks. This is a diagram. It's the metamorphic facies diagram. And notice that on the horizontal axis, we have temperature. So temperature is increasing to the right. Higher temperatures to the right, lower temperatures to the left. And then vertically, we have depth. That's the same thing as pressure in the sense that as you go deeper and deeper into Earth's interior, both depth and pressure are increasing. Nothing really to memorize about this diagram. I really just included it so you can appreciate that we get different index minerals depending on the pressures and the temperatures at which metamorphism is occurring. As a couple of examples, if we're not very hot and we're not very deep, we might end up with a metamorphic facies known as the zeolite facies. However, what if we're at a much higher temperature, way over here, 600 degrees centigrade, and we're really deep. We're on the order of 25 or 30 kilometers in depth. Then we're in what's called the amphibolite facies. Amphibolite facies rocks are going to have very different index minerals in them than zeolite facies rocks. That's the main take-home message of this diagram, is that we can, in effect, reconstruct the temperature and pressure history of the rock by looking at these characteristic index minerals in the rock, which lead us to infer the metamorphic facies we're in. Okay, this slide just illustrates the fact that even at a single plate boundary environment, a subduction zone in this case, we have differing metamorphic conditions. And again, nothing to memorize on this diagram. I just want you to appreciate that within different regions of this one subduction zone, we have different pressure and temperature conditions, different metamorphic facies. We're ultimately going to get different kinds of metamorphic rock. So here, for example, we're not very deep, so we have relatively low pressures and also low temperatures. That's going to give us zeolite facies rocks. On the other hand, maybe if we're right here, we're still not very deep, but we're really hot. Why are we hot? Because we're very close to the edges of that hot magma body that's migrated up from below. That's going to give us Hornfels facies. And by the way, this type of metamorphism, where the rocks are being baked due to proximity to a magma body, is called contact metamorphism. So Hornfels facies rocks are characteristic of low pressure, high temperature, that is thermal metamorphism, near magma bodies, and collectively that style of metamorphism is known as contact metamorphism because the rock is being changed due to the fact that it's in contact with a hot magma body. And here, where I'm circling now, we're down deep in the subduction zone. So because we're deep, we have high pressure. Also because we're deep and because we're in close proximity to these magma bodies, we have high temperature. That's going to lead to yet different kinds of minerals growing in the rock, those characteristic of granulite facies. And then finally, perhaps the strangest situation of all is where we're relatively deep inside the subducting plate or directly adjacent to the subducting plate. So because we're deep, we get high pressure, but because the subducting plate is cold to begin with, we get lower than expected temperatures for the depth that we're at. And that gives us a really distinct metamorphic facies, high pressure but lower than expected temperatures, called blue schist. So let me get rid of this annotation here and I'll show you examples of the rocks associated with different parts of this subduction zone. So here at high pressure, low temperature, we get a distinctive type of rock actually called blue schist. It's called blue schist because the high pressure, low temperature minerals that have grown in the rock are literally blue. Elsewhere in the subduction zone, if we're really, really deep, we get high temperatures and high pressures. We get a rock that starts to resemble granite, and it's called granulite. You can see that this rock actually has a bit of a gneissic texture. We see that light and dark banding in the rock that's generally characteristic of high pressures and high temperatures. And then again, up here at shallow depth, directly adjacent to that hot magma body, we get this sort of dark colored, very fine grained metamorphic rock called Hornfels. And again, Hornfels is characteristic of contact, that is thermal metamorphism, typically at low pressure, which means you're pretty shallow. And then finally, zeolite facies rocks occur at relatively low pressures and low temperatures that we might encounter just right around the trench, for example, in the subduction zone. We can also get metamorphism at collision zones. And in this case, we can get a whole host of foliated metamorphic rocks. And again, as depth and temperature increase, we may transform the rock from slate to phyllite to schist to gneiss. It's fair to say that most foliated metamorphic rocks occur at convergent boundaries, that is, subduction zones and also collision zones, but we also get metamorphism at divergent boundaries as well. I was kind of talking about this earlier. Metamorphism in the presence of abundant water. That's called hydrothermal metamorphism. And you can read about it here. Cold seawater is percolating into the mid-ocean ridge. It gets close to the magma at a relatively shallow depth. It then warms up and migrates back up to the surface, metamorphosing the igneous rock in the process. And it's this overall divergent plate boundary environment that produces serpentinite, which is the state rock. And we can even get a sort of mechanical version of metamorphism at transform boundaries. So here we have, one plate moving laterally that way, another plate moving laterally that way. And in this area in between, we have sort of a mush zone. We have sort of a zone of intense shearing and smearing. And what happens to the minerals in the rock within the zone of shearing and smearing is they kind of become smeared out and flattened. So we're actually here producing a rock with a little bit of a gneissic texture, but in this case, the gneissic texture isn't so much a result of compressive stress alone, it's produced by intense shearing. So the take-home message here is, in general, we tend to get metamorphism at plate boundaries, at convergent, divergent, and transform plate boundaries. Let's do another concept check question. Study the ocean continent subduction zone diagram below. At which location would you expect the temperature to be the lowest? So I'll give you a few seconds to decide what you think is the right answer. All right, hopefully you picked location 1, because again, location 1 is in the cold subducting plate, as opposed to location 2, which is in the non-subducting plate. So even though locations 1 or 2 occur at the same depth, the rocks are cooler at location 1 than at location 2, because at location 1, they're embedded within the subducting plate, which is cooler to begin with. And another concept check. At which plate boundary setting would you expect high pressure, low temperature metamorphism to occur? What do you think? Like we talked about a few slides ago, we tend to get this rather bizarre style of metamorphism at subduction zones because in this case, we're deep enough that we have high pressure. And at those depths, we might also expect high temperature, except in this particular environment, we're embedded within a relatively cool plate. And at this point, the plate hasn't yet warmed up very much. And so even at those relatively great depths, we have a low temperature because the plate is cooler to begin with. And another concept check. At which geologic setting would you expect low pressure, high temperature metamorphism? So here we're kind of reversing what we did in the last question, low pressure, high temperature. I'll give you a couple seconds here to decide. Okay, here's how I would approach this question if I got it on an exam. I would remember that low pressure in general is going to mean that we're pretty shallow. We're at a relatively shallow depth because if we were deep, no matter where we were, pressure would be high. So because the pressure is low, we can automatically rule out the questions that tell us, or the answers that tell us that we're deep in Earth's interior. So great, we now only have to choose between B and D. B, are we near Earth's surface, far from a magma body? Well, if we're near Earth's surface, sure, pressure would be low, But if we're far from a magma body, temperature would also be low. So it's probably not B. What about near Earth's surface, near a magma body? That's going to give us the right conditions. If we're near Earth's surface, pressure is going to be low. And if we're near a magma body, temperature is going to be high. So, of course, the correct answer is D. Near Earth's surface, near a magma body is where we have both low pressure and high temperature conditions. It's, again, near magma bodies that we get a style of metamorphism known as contact metamorphism. Okay, well, let's summarize this entire presentation in terms of what you really need to focus on. Make sure you can define metamorphism. That's covered very nicely in the first slide of this presentation. Make sure you understand what factors control metamorphism, and also review what sorts of specific changes accompany the metamorphic process. That's covered very early in this presentation. You want to become pretty familiar with the common foliated and non-foliated metamorphic rocks, and certainly we've covered that as well in today's presentation. You want to understand the distinction between pressure and stress. Very, very important. But that's easy, right? Pressure is equally applied in all directions, whereas stress is simply unequally applied pressure, where the pressure is greater in one particular direction than in any other direction. And obviously, we tend to get stresses concentrated at plate boundaries in general, as opposed to far away from plate boundaries. And then you want to be familiar with various metamorphic conditions in terms of pressure and temperature. Don't worry about memorizing that metamorphic facies diagram. I just want you to know, for example, that if you're down deep and not within a subducting plate, you're going to generally experience high pressure and high temperature. If you're within a subducting plate, even if you're down deep, the temperature is going to be lower than expected for how high pressures are. And if you're at a shallow depth near a magma body, pressures are going to be low because you're not very deep, but temperature is going to be high because you're close to the magma body. Okay, that's it for this presentation on metamorphic rocks.